physicists built a theory so precise it can predict the behavior of a single electron to 12 decimal places. 12, that is like measuring the distance from New York to Los Angeles down to the width of a single human hair. We call it quantum field theory, and it powers every atom smasher, every atomic clock, every microchip on Earth. And yet the same math that gets it right also predicts that empty space should contain enough energy to have shredded the universe before a single star ever formed. We are going to walk through the broken heart of physics together, from invisible fields boiling underneath your feet to a $1 million math prize no one can claim, to the moment scientists realized they were calculating the universe using imaginary numbers. If you enjoy the journey, subscribe and hit like. Let's go. Stand completely still for a moment. You feel solid. The floor under you feels solid. Everything around you looks like a collection of objects, separate and distinct. A chair is a chair. Your hand is your hand. Physics says something very different. Everything you see, touch and breathe is a vibration, a ripple, a disturbance moving through something invisible that stretches across the entire universe. Physicists call these quantum fields. They are not objects you can hold or point to. They are more like the surface of an ocean spread out everywhere all at once. When that ocean surface shakes in a particular spot, we perceive that shake as a particle. An electron is a ripple in the electron field. A photon, a particle of light, is a ripple in the electromagnetic field. Every kind of particle in existence is just a different type of vibration in a different type of field. These fields are not local. They do not sit in one place. Every field stretches across the entire observable universe, from here to the farthest galaxy we can detect, about 46 billion light-years away. When something disturbs a field right here, the rules of quantum mechanics govern what happens next. Right now, multiple fields are passing through your body. The electromagnetic field is there, the electron field, the Higgs field, which gives particles their mass. You are not sitting inside empty space. You are swimming inside a dense, layered stack of invisible fields that exist everywhere simultaneously. This is the foundation of what physicists call quantum field theory. It replaced the old picture of particles as tiny billiard balls bouncing around in empty space. That picture broke down in the early 20th century when experiments showed that particles behave like waves spread out across space, interfering with themselves, existing in multiple places at once until the moment they are measured. Fields solved that puzzle. A ripple in a field naturally behaves like a wave. The framework that came out of this thinking became the most tested scientific theory in history. When researchers use it to calculate the magnetic spin of an electron, they get a number that matches laboratory measurements out to 12 decimal places. To picture that kind of precision, imagine predicting the driving distance from New York to Los Angeles over 2,700 miles and landing within 1 millimeter of the right answer. Every single time. No other scientific theory in any field, chemistry, biology, engineering, comes anywhere close to that level of accuracy. Quantum field theory works. It works staggeringly well. Particle accelerators around the world depend on its equations to predict exactly what will happen when subatomic particles crash into each other at nearly the speed of light. The predictions match. Always, and yet physicists are quietly terrified, because when you look past the accurate predictions and stare directly at the math underneath, the equations start screaming. They return values that make no sense, infinite values, impossible values. Answers so catastrophically wrong that if they were correct, you would not exist. The planet would not exist. The universe itself would have been torn apart before a single hydrogen atom had time to form. The theory that describes everything we can see and measure is, at its deepest level, mathematically broken. Scientists have known this for decades. They have clever workarounds that make the math usable. But the underlying crack has never been fixed. And the further you zoom in on it, the stranger and more disturbing it gets. Every field that passes through you right now is part of a system that nobody fully understands. You are built from ripples in something nobody can fully explain. And the emptiness between those ripples, that is where things get genuinely unsettling. In 1947, a physicist named Willis Lamb measured something that should not have been there. He was studying hydrogen atoms, and he found a tiny gap between two energy levels inside the atom. A gap that the existing equations said should be exactly zero. The gap was real. The equations were wrong. That single measurement cracked open a revolution in physics. The crisis forced a group of the sharpest minds in the world to completely rethink how quantum mechanics and electromagnetism work together. Out of that effort came quantum electrodynamics, the first and most precise version of quantum field theory ever constructed. The test case was simple on paper. Calculate the magnetic properties of an electron. Specifically, calculate something called the magnetic moment, a measure of how strongly an electron behaves like a tiny spinning magnet. The calculation involves accounting for every way the electron can interact with the electromagnetic field around it, including the virtual particles constantly flickering in and out of the vacuum nearby. The math is savage. Even with the cleanest version of the calculation, physicists fill entire notebooks with diagrams and equations before arriving at a single number. Richard Feynman developed a visual shorthand, little diagrams that look like stick figures, each one representing a specific interaction. But behind every diagram sits a wall of calculus so dense that completing the full calculation at high precision took teams of researchers years of work. The number they arrived at, after all of that, is 2.0023193713. The number measured directly in the laboratory is 2.0023193712. The difference between prediction and measurement is smaller than 1 part in a trillion. That gap is like measuring the distance across the entire United States, coast to coast, about 2,800 miles, and being off by less than the thickness of a single sheet of paper. No experiment in chemistry, astronomy, biology, or engineering has ever come close to this level of match between theory and reality. Physicists call it the jewel of physics. It is the single most accurate prediction any human theory has ever made. So why is anyone worried? Because the same framework that produces this miracle also demands that the electron has an infinite mass. Before that 12 decimal place answer pops out, the raw equations return infinity. Physicists have to perform a mathematical procedure to strip that infinity out before the usable number appears. They call this renormalization, and renormalization, for all its success, is widely understood as a patch on a deeper wound. Feynman himself, the man who won the Nobel Prize partly for developing the tools that make these calculations possible, once called the technique hocus pocus. He said, publicly and on the record, that renormalization was not mathematically justified. He believed the theory was getting the right answers through a process that disguised a fundamental error rather than solving it. The precision is real. The 12 decimal places are real. But they are built on a foundation that one of the method's own inventors called a trick. And if the most elegant prediction in science is secretly resting on a trick, then the question of what is actually underneath has never been answered. The answer to that question involves something even stranger than infinities. It involves the vacuum of space itself turning out to be anything but empty. Picture a perfect vacuum. A sealed box with every last molecule of air sucked out. No light, no heat, no atoms. Nothing. Now picture that box exploding with activity. Quantum field theory says that is exactly what is happening inside every vacuum, including the ones in the most advanced physics labs on Earth. Empty space is a battleground. Pairs of particles appear out of nowhere, exist for a fraction of a second so short it cannot be measured directly, and then collide and annihilate each other, vanishing just as fast. These are called virtual particles. They are not imaginary. They have real, measurable effects on the atoms around them. The energy they carry shifts the behavior of electrons in ways that can be detected in the laboratory. That shift is part of what Willis Lamb measured in 1947. The gap he found was caused, at least in part, by virtual particles flickering in and out of the vacuum around the hydrogen atom. So the vacuum is not empty, it is boiling. The electromagnetic field alone is responsible for producing these virtual flickers in empty space. Pairs of virtual electrons and their antimatter partners, called positrons, pop into existence, interact briefly with real particles nearby, and then disappear. The strong nuclear field does the same thing with its own particles. Every quantum field contributes to the constant churn of the vacuum, layering wave upon wave of short-lived activity on top of what looks, from a distance, like nothing. This is not a fringe idea. It is central to how quantum field theory works. The vacuum is a participant in every physical process. When an atom releases a photon of light, the vacuum plays a role. When two magnets attract, the vacuum is involved. The emptiness between particles is an active, structured, energy-carrying environment. Scientists can measure this in a striking way. Place two metal plates very close together, within a millionth of an inch of each other, in a perfect vacuum. The virtual particles between the plates are restricted to certain wavelengths by the gap. Outside the plates, more wavelengths of virtual activity are allowed. That imbalance creates a tiny, but real physical force pushing the plates together. This is called the Casimir effect, and it has been measured directly in the laboratory. The vacuum pushed the plates. Emptiness created a measurable force. If virtual particles were a fantasy, the Casimir effect would not exist. It does. Now here is the problem. If the vacuum contains all this energy, every quantum field contributing its own flickering activity across the entire universe, how much total energy does the vacuum actually hold? Physicists ran the calculation. The answer came back as a number so enormous it does not fit inside normal human intuition. The math predicted that the energy density of empty space should be astronomical. Universe-destroying levels of energy, sitting quietly in every cubic inch of what looks like nothing. And yet, here we are. The universe exists. Stars form. Galaxies spin. Life happens. The difference between what the math predicts and what we actually measure is the single largest error in the history of science, and the deeper you look at it, the worse it gets. The calculation seemed routine. Physicists already knew the vacuum was full of activity. Every quantum field contributes energy to empty space. So a team sat down to calculate the total. Add up every contribution from every known field. Find the energy density of the vacuum. Compare it to the measured value. Simple. The number that came out was catastrophic. The math predicted that the energy contained in empty space should be 10 followed by 120 zeros times larger than what we actually measure. Written as a number, that looks like a 1 with 120 zeros after it. That number is incomprehensibly large. The total number of atoms in the entire observable universe is only about 10 followed by 80 zeros. The error in the vacuum energy prediction dwarfs that by 40 orders of magnitude. To put it another way, if the vacuum energy were actually what the equations predict, the universe would have been ripped apart before the first second of its existence. Every atom, every photon, every ripple in every field would have been flung apart at speeds so extreme that nothing could ever form. No stars, no planets, no chemistry, no you. This failure has a name. Physicists call it the vacuum catastrophe, and it is widely acknowledged as the most embarrassing mismatch between theory and observation in all of science. One of the most brilliant and well-tested theories ever built makes, at the same time, one of the most spectacularly wrong predictions ever recorded. The troubling part is not just that the prediction is wrong. The troubling part is that no one knows why it is wrong. Scientists have proposed dozens of explanations over the decades. Some argue there must be a hidden symmetry in nature, a cosmic balancing act that quietly cancels out most of the vacuum energy before it can affect the universe. This idea is called supersymmetry. and it predicts that every known particle has a twin partner particle with slightly different properties. If those partners exist, their contributions to the vacuum energy would cancel against the contributions of ordinary particles, bringing the total down dramatically. The problem? Decades of searching at particle accelerators around the world have found zero evidence of any supersymmetric partner particles. Not one. Others suggest the answer lies in dark energy, the mysterious force driving the universe to expand at an accelerating rate. The measured energy of empty space, which is extremely small but real and non-zero, matches what dark energy requires. But connecting that measured value back to the quantum field prediction requires explaining where all the predicted energy went. And no one has that explanation. Some physicists have begun suggesting something even more unsettling. Maybe the equations themselves are fundamentally pointing at a gap in our understanding of reality. A place where our current description of nature simply stops working. They might be right. Because the vacuum catastrophe is not the only place where the math breaks down. There is another problem, one that does not involve the vacuum at all, one that involves a force every person on Earth has felt their entire life, and it has been completely left out of the equations from the very beginning. Scientists are careful with language. They measure twice, check their math, and recheck their assumptions before claiming anything. So when physicists look at the vacuum energy prediction and call it the worst prediction in the history of science, that statement carries real weight. Let us try to make that error feel real, because a number with 120 zeros in it does not naturally land in human intuition. Start with a yardstick. Now imagine shrinking that yardstick down by a factor of 10. Then by 10 again. Keep going. After 35 halvings, you are at the scale of a single proton, the dense core sitting in the heart of every atom. That is inconceivably small. Now imagine the reverse. Start at the size of an atom and scale up by the same steps. After about 80 of those steps, you have crossed the entire observable universe, roughly 93 billion light-years across. The error in the vacuum energy calculation is larger than that entire range, compressed into a single number. If you printed the predicted vacuum energy on one side of a scale and placed every atom in the observable universe on the other side, the predicted vacuum energy would outweigh the universe by a factor larger than the universe itself. That is the gap between theory and reality. And the theory is the most successful physics framework ever built. Here is what makes this even stranger. The measured value of vacuum energy is not zero. Scientists have measured it. The universe is expanding at an accelerating rate, and that acceleration requires some energy to be present in empty space. The measured amount is tiny but real. Cosmologists call it dark energy, and it accounts for roughly 68% of the total energy content of the universe. So the vacuum does have energy. The measurement is real. The issue is that the predicted value and the measured value disagree by that enormous factor. Something is cancelling out almost all of the predicted vacuum energy, leaving only a tiny residue. That residue, dark energy, is driving the expansion of the universe. The cancellation required to get from the predicted number down to the measured one is so precise it staggers physicists. Imagine a lottery where the jackpot is 10 followed by $120. Now imagine someone wins, but after taxes, they take home exactly $1. The cancellation required to go from the jackpot to $1 across that many orders of magnitude would have to be deliberate, engineered, and impossibly exact. If it is accidental, it is the most staggering coincidence in the history of science. If it is deliberate, something in nature is performing a cosmic balancing act that no current theory can explain or predict. Either way, the math is telling us something is fundamentally missing from our picture of reality. The fields are real, the vacuum activity is real, but the rules governing how much energy all of that activity produces are either wrong or massively incomplete. And while physicists wrestle with that catastrophe, there is a separate, equally deep problem hiding in the foundations of quantum field theory itself. A problem that predates the vacuum catastrophe. A problem that Feynman himself refused to accept as a real solution. Forget particles for a moment. Every particle physics textbook ever written starts with the wrong picture. It shows electrons as tiny dots, protons as slightly bigger dots, photons as little packets of energy zipping through space. That picture helped build the atomic bomb and design the microchip. It also happens to be fundamentally inaccurate. A quantum field is something entirely different from a particle. Picture the surface of the ocean. The water stretches everywhere. There is no hard edge, no boundary where the ocean stops. Now imagine dropping a stone into that ocean. A ripple spreads outward from the point of impact. That ripple has energy. It moves, it interacts with other ripples. But the ripple is not a separate thing from the ocean. It is the ocean, moving in a particular way. Electrons work the same way. There is one electron field, and it stretches everywhere in the universe. Every electron in existence is a localized vibration in that single field. There is no such thing as a standalone electron floating in empty space. There is only the field, and a disturbance moving through it. The same goes for every known particle. The photon field carries light. The quark fields make up the interior of protons and neutrons. The Higgs field, confirmed by the Large Hadron Collider in 2012, gives other particles their mass by interacting with them as they move. Every force and every particle is a field, and those fields overlap everywhere all at once, filling all of space simultaneously. Now here is what makes this genuinely strange. These fields exist even when nothing is happening in them. A completely calm ocean surface is still an ocean. In the same way, even a field with no particles moving through it, even a field in its lowest energy state, still exists and still has properties. That minimum energy state is called the ground state or the vacuum state. And that vacuum state is where the problems begin, because when physicists calculate what happens in those calm, empty fields, they discover the fields are never truly calm. Quantum mechanics forbids it. The same principle that makes it impossible to know both the exact position and the exact speed of a particle also makes it impossible for a field to sit perfectly still at zero energy. There is always a minimum jitter, always a tiny fluctuation built into the foundation of the field itself. That jitter is the source of the virtual particles discussed earlier, and the energy of that jitter, summed up across all the fields that fill the universe, is the source of the vacuum catastrophe. So the very foundation of quantum field theory, the ground state of the fields themselves, is generating a prediction that breaks the universe on paper. Physicists have lived with this problem for decades. Their practical solution is to ignore the absolute energy of the vacuum and focus only on the differences in energy between states. That approach works for most calculations. It produces the 12 decimal place electron prediction. It powers particle accelerators. It builds the standard model of particle physics. And the standard model is in many ways the most ambitious and successful structure in all of science. But it has holes, large ones, and one of them has been visible from the very first day the model was assembled. In the 1960s and 70s, physicists accomplished something remarkable. They took everything known about particles and forces and organized it into a single framework. They called it the Standard Model. It describes every known particle, every force that acts between them, and the fields that carry those forces. Everything except one. The Standard Model identifies 12 fundamental particles of matter. 6 are called quarks, and they build the protons and neutrons inside every atom. 6 are called leptons, and they include the electron and its relatives. It also describes 4 fundamental forces and the particles that carry them. Photons carry electromagnetism. Gluons carry the strong nuclear force that holds the interior of atoms together. The W and Z bosons carry the weak nuclear force responsible for certain types of radioactive decay. And the Higgs boson gives other particles their mass. When physicists at the Large Hadron Collider confirmed the existence of the Higgs boson in 2012, every particle predicted by the Standard Model had been found. Every prediction had been verified. It was one of the greatest scientific achievements of the 20th and 21st centuries combined. And yet the Standard Model describes only about 5% of the mass and energy in the universe. The other 95% sits outside its equations entirely. Dark matter, the invisible substance responsible for the extra-gravitational pull that holds galaxies together, does not appear anywhere in the Standard Model. Dark energy, the force driving the accelerating expansion of the universe, has no place in the model. The model does not explain why there is more matter than antimatter in the universe. It does not explain why neutrinos, particles once thought to be massless, actually have a tiny but real mass. And most critically, the Standard Model says absolutely nothing about gravity. Not approximately nothing. Literally nothing. The force that holds you to the surface of the Earth, that keeps the Moon in orbit, that shapes the large-scale structure of the entire universe, appears nowhere in the Standard Model's equations. This is not because physicists forgot. They have been trying to include gravity for decades. The problem is that every attempt to add gravity to the quantum field framework produces equations that immediately explode into meaningless infinities that cannot be removed using the same renormalization tricks that work for the other forces. Gravity, it turns out, refuses to play by the same rules, and the deeper physicists dig into why, the more they realize the problem is not a missing piece that can be added later. It points to something more fundamental, something about the structure of space and time itself that quantum field theory simply cannot capture. What happens when physicists actually try to merge gravity with quantum fields? The answer is something that sounds almost impossible. Every other force in nature has been brought inside the quantum field framework. Electromagnetism was quantized in the 1940s, producing quantum electrodynamics, that extraordinarily precise theory of light and electrons. The weak nuclear force was unified with electromagnetism in the 1960s and 70s. The strong nuclear force was captured by a quantum field theory called quantum chromodynamics. Each of these unifications was difficult. Each required years of work, new mathematical tools, and Nobel Prizes. Gravity has resisted every attempt. The reason comes down to a fundamental mismatch between two different descriptions of reality. Einstein's theory of general relativity describes gravity as the curvature of space-time. Mass bends the fabric of space and time around it. Other objects follow the curves in that fabric, and we experience that as the force of gravity. The Earth curves space around it. The Moon follows that curve. You follow that curve every time you drop something and watch it fall. General relativity is a smooth theory. It describes space-time as a continuous, flexible surface, like a rubber sheet that can be stretched and warped. There are no sudden jumps, no minimum units of curvature. Space curves gently and predictably. Quantum field theory is the opposite. It is a choppy, discrete theory. Energy comes in minimum units called quanta. Fields jump and fluctuate. Nothing is perfectly smooth. Everything has an underlying graininess at the smallest scales. When physicists try to apply quantum field rules to gravity, they have to introduce a hypothetical particle that carries the gravitational force, just like photons carry electromagnetism. This particle is called the graviton. And when they calculate what happens when gravitons interact with each other, the equations return infinities that cannot be removed by any known mathematical technique. The renormalization tricks that saved quantum electrodynamics from its infinite answers simply do not work for gravity. When you try to remove one infinity from the graviton equations, you create several new ones. Remove those, and you create more. The problem multiplies without end. The theory is what mathematicians call non-renormalizable. This is not a small technical problem waiting for a clever fix. Many physicists believe it points to something deep. Quantum field theory may be built on assumptions about the nature of space that are only approximately correct. At the smallest conceivable scale, roughly 100 billion times smaller than a proton. A scale so tiny it makes the proton look like a galaxy by comparison, space-time itself might stop being smooth. It might become a chaotic, churning foam where the rules of both general relativity and quantum field theory break down simultaneously. No one has ever measured anything at that scale. Existing instruments are not even remotely close to reaching it, but the mathematics strongly suggests something radical happens there. And every time physicists try to fix the problem with gravity, they end up needing a trick, a mathematical sleight of hand that makes the equations usable without actually solving the underlying problem. Feynman's renormalization was one such trick, and Feynman himself had serious doubts about it from the very beginning. The year was 1947. The equations were beautiful, and they were broken. Physicists had assembled quantum electrodynamics, the quantum field theory of light and electrons. It described how electrons emit and absorb photons, how light interacts with matter, how atoms hold themselves together. The structure was elegant, the logic was sound. Then someone tried to calculate the mass of an electron. The answer came back as infinity. This was not a rounding error or a small numerical mistake. The math genuinely returned an infinite value. When physicists calculated how much energy the electromagnetic field surrounding an electron contributes to the electron's mass, the sum kept growing without limit. Every step added more. The total never settled on a finite number. The same thing happened with the electric charge of the electron. Calculate how the vacuum fluctuations around an electron affect its charge, and the answer explodes toward infinity. Physics cannot work with infinite answers. Experiments produce finite numbers. Detectors measure specific values. A theory that outputs infinity for the most basic properties of the most common particle in the universe is, by any practical definition, broken. So physicists invented a workaround. They called it renormalization. The idea works like this. The raw, unregulated equations produce an infinite bare mass for the electron. But the electron also interacts with its own electromagnetic field, which produces another, opposite contribution to its effective mass. Renormalization takes these two infinite quantities and demands that they combine to produce the finite measured mass of the real electron. The infinities cancel. What remains is the number you see in the laboratory. Mathematically, this requires treating the raw mass as a free parameter and adjusting it so the final answer matches experiment. You are, in essence, defining the electron's properties by what you measure, rather than deriving them purely from theory. The infinities are absorbed into the definition and hidden. It works. The predictions that come out after renormalization are extraordinary in their accuracy. The 12 decimal place electron prediction comes from a renormalized calculation. And yet, Feynman, who developed some of the core tools of renormalization and won the Nobel Prize for his contributions to quantum electrodynamics, called the process hocus pocus in print. He wrote that no one had actually solved the infinity problem. They had found a systematic way to sweep it under the rug. Other physicists agreed. Paul Dirac, the brilliant British physicist whose equations first predicted the existence of antimatter, called renormalization an ugly procedure and insisted until his death that a genuinely correct theory would not require it. The predictions are real, the underlying mathematics is patched, and the patch holds together the most accurate theory in the history of science. That patch needed a visual tool to make it manageable. The tool Feynman invented for it became famous. It looks like something a 10-year-old would doodle. It hides something a supercomputer strains to process. Look at a Feynman diagram and you will think you are looking at a simple sketch. Lines going in, lines going out, a few squiggly lines connecting them in the middle, arrows showing direction. It looks like a map of subway stops, or maybe a rough doodle from the margins of a student's notebook. It is one of the most powerful and deceptive objects in all of science. Each Feynman diagram represents a specific way that particles can interact. An electron moving through space emits a photon. That photon travels a short distance. Another electron absorbs it. The two electrons push apart. That interaction, the electromagnetic repulsion between two electrons, can be drawn as one simple diagram. Two lines coming in, a squiggly line in the middle, two lines going out. That one diagram represents a calculable process. The calculation involves plugging numbers into quantum field theory equations and following strict mathematical rules. The result gives you the probability of that specific interaction happening. But one diagram is never enough. In quantum field theory, every possible way an interaction can happen contributes to the final answer. There are infinitely many possible diagrams for any given interaction. The electron might emit two photons instead of one. One of those photons might briefly split into a virtual electron-positron pair before recombining. That pair might emit another photon. And so on, branching outward into increasingly complicated networks of interactions. Each additional diagram is more mathematically complex than the last, and each one contributes a smaller amount to the final answer. So physicists can get increasingly precise results by calculating more and more diagrams. The one diagram calculation for two electrons repelling each other fills roughly one page of mathematics. The 10 diagram calculation fills several rooms worth of paper. The calculation required to achieve the 12 decimal place electron magnetic moment involved evaluating over 10,000 distinct Feynman diagrams, each one a separate calculation, many of them requiring supercomputers running for months. The diagrams look like stick figures. The mathematics behind them looks like the interior of a particle accelerator. And here is the part that troubled Feynman himself. Many of those diagrams, especially the ones involving loops in the middle where particles circle back on themselves, produce infinite answers before renormalization is applied. Those loops represent particles interacting with their own fields over arbitrarily short distances, and at those short distances the equations stop behaving. The infinities pour out. Renormalization handles those loops by absorbing the infinities into the measured quantities of the particles, the mass, the charge, the coupling strength. It works. The final answers match experiment, but the process is, as Feynman put it himself, a way to hide what we do not understand behind what we can measure. The diagrams are beautiful. They are also built to bypass a catastrophic flaw in the theory they represent. That flaw has a specific mathematical form, and in the year 2000, a group of mathematicians put a $1 million prize on the table for anyone who could prove that flaw even exists in a rigorous, complete way. No one has claimed it yet. In the year 2000, a group called the Clay Mathematics Institute listed 7 mathematical problems. They called them the Millennium Prize Problems. Solve any one of them, and they would pay you $1 million. 6 of the 7 involve pure mathematics. Number theory, topology, fluid dynamics. Abstract puzzles with no obvious connection to the physical world. One of them sits at the heart of particle physics. It is called the Yang-Mills existence and mass gap problem, and it is, quietly, one of the most important unsolved questions in science. Here is the problem. The equations that describe the strong nuclear force, the force that holds quarks together inside protons and neutrons, are built on a mathematical structure called Yang-Mills theory. This structure was developed in the 1950s. Physicists have been using it ever since. It produces predictions that match experiments at particle accelerators around the world. The theory works in practice. The problem is that no one has ever proven it works in principle. No mathematician has ever shown, using strict mathematical logic, that the quantum version of Yang-Mills theory actually exists as a consistent mathematical object, and no one has proven the mass gap. The mass gap refers to a specific feature of the strong nuclear force. In nature, the particles that carry the strong force, called gluons, are never found alone. They are always bound inside larger particles. There is a minimum energy required to create a free, isolated particle from the strong force fields. That minimum energy is the mass gap. The fact that the mass gap exists is confirmed by decades of experiment. You cannot find an isolated gluon in a particle accelerator. The gap is real. But no one can prove it mathematically from the base equations of the theory. The equations are written. The predictions match reality. And yet the mathematical foundation is not solid. It is a framework resting on ground that no one has certified as stable. To a physicist, this is uncomfortable but livable. The equations work. The experiments match. Move forward. To a mathematician, this is deeply alarming. A theory with no proven mathematical foundation is not a theory in any rigorous sense. It is a highly successful conjecture. And science built on unproven conjecture is, at some level, science built on faith. The $1 million prize has sat unclaimed for over 25 years. Teams of mathematicians have attacked the problem. Several have published papers claiming progress. None have cleared the full bar required for the prize committee to award the money. The proof, if it exists, requires mathematical machinery that may not have been invented yet. And the failure to find that proof means that the most fundamental description of how matter holds itself together is, mathematically speaking, sitting on a foundation that has never been verified. Something even stranger waits inside those equations. Something about what happens when you try to pull apart the particles the strong force holds together. Every proton in the universe is a prison. Inside each proton sit 3 quarks, the fundamental particles that make up all nuclear matter. They are held together by the strong nuclear force, carried by particles called gluons. The quarks are not gently attached to each other. They are bound with a force so extreme that the more you try to pull them apart, the stronger the force between them becomes. Picture a rubber band. Stretch it a little, and it pulls back gently. Stretch it further, and it pulls harder. Keep stretching, and eventually it snaps. That is roughly how most forces work. Increase the distance, and at some point the force breaks. Quarks do not work this way. The strong force between quarks actually grows stronger as the distance between them increases. Pull 2 quarks apart, and the force pulling them back builds. You add energy to the system by pulling. More energy. More energy. Until something unexpected happens. At a certain point, you have put so much energy into the gap between the quarks that the energy itself spontaneously creates a new pair of quarks out of the vacuum. A quark and an antiquark materialize from the energy you fed into the field, and they immediately attach to the original quarks. You tried to pull 1 quark free. Instead, you created 2 new ones and ended up with 2 bound pairs instead of 1. This process is called quark confinement. It means a free, isolated quark has never been observed in any experiment. Every attempt to produce one just generates more quarks. The quark is perpetually trapped no matter how much energy you throw at the problem. The energy required to snap a quark free is effectively infinite in practical terms, because the field keeps converting that energy into new particles before any separation can occur. This also means that every proton you have ever touched, in every object on Earth, contains quarks that have been trapped since the first microseconds after the Big Bang. They have never been free. They will never be free under any conditions that exist naturally in our universe. Quark confinement is confirmed beyond any doubt by experiment. But the mathematical proof of why it happens, why the strong force has this behavior built into it at a fundamental level, is the same thing the $1 million Yang Mills Prize is asking for. The equations predict confinement works. They do not prove why confinement must be. The gap between what the math produces and what the math can explain is enormous. And the vacuum, that boiling sea of virtual particles, plays a crucial role in the confinement process. When you try to pull quarks apart, the vacuum does not sit still. It participates. It responds. It generates new particles to fill the gap. This means the vacuum is not just a passive backdrop to particle physics. It is an active player, responsive and creative. It generates matter from energy on demand. That same vacuum and the fields running through it turns out to be the stage for something even more ambitious and more troubling: the attempt to describe all of reality in one single set of equations. The infinities that haunt quantum field theory have a specific origin. When two particles interact at a point, a single mathematical point with no size, the equations cannot handle it. A point interaction involves dividing by zero in a disguised form. The result is infinity. Renormalization patches it, but the patch is not a solution, it is a cover. In the 1980s, a radical idea spread through the physics community. What if particles were not points? What if the fundamental objects of nature were tiny, one-dimensional strings, loops and strands of energy too small to see with any instrument, vibrating at different frequencies? The idea sounds simple. Its consequences are enormous. If particles are strings, then their interactions are no longer point collisions. Two strings approaching each other merge gradually, like two soap bubbles touching and joining. That gradual joining spreads the interaction across a tiny region of space instead of a single mathematical point, and that spreading eliminates the infinities. The division by zero never happens. The calculation stays finite. String theory also does something quantum field theory cannot. When physicists work out the mathematics of vibrating strings, one of the vibrational modes that naturally appears in the equations corresponds to a massless particle with a specific spin. That particle's properties exactly match the graviton, the hypothetical particle that would carry gravity. String theory did not set out to explain gravity. Gravity fell out of the math uninvited. For many physicists in the 1980s, this felt like a moment of breakthrough. A theory that eliminates the infinities of quantum field theory and automatically includes gravity looked like the path to a unified description of all forces and all particles. The catch came quickly. For string theory's mathematics to be consistent, without producing internal contradictions, space cannot have just 3 dimensions. The equations require 10 dimensions of space and 1 of time, for a total of 11 dimensions of reality. We experience only 4, 3 of space and 1 of time. The other 6 or 7 dimensions, if they exist, must be curled up at scales so tiny that no current instrument can detect them. This is not a choice in string theory. The extra dimensions are forced on you by the math. Remove them and the equations fall apart. No one has ever detected an extra dimension. Experiments at the Large Hadron Collider searched for signs of them and found nothing. They may be too small to ever be observed directly. They may not exist at all. String theory's promise, a theory that unifies everything and eliminates the infinities, requires a version of reality that no experiment has confirmed. That tension has divided the physics community for decades. And the extra dimensions are only the beginning of the problem. String theory has a landscape problem. The 6 extra dimensions required by the theory cannot simply exist in any shape. They have to be curled up, folded, and wrapped around themselves in specific geometric configurations. Different configurations produce different universes with different physical laws. When mathematicians calculated how many distinct configurations are possible, the number they arrived at was 10 followed by 500. To understand the scale of that number, the total number of atoms in the observable universe is approximately 10 followed by 80. The number of distinct string theory universes is so much larger than the number of atoms in our universe that comparing them feels meaningless. You would need universes full of atoms just to start approaching it. Each of those possible configurations produces a different set of physical constants, different strengths for gravity, different masses for the electron, different values for the speed of light. In almost all of them, the laws would not allow stars to form, atoms to hold together, or chemistry of any kind to operate. Only a tiny fraction of the possible universes would look anything like ours. This creates a profound problem. String theory, which was supposed to be a unique framework that predicts our universe from first principles, instead produces an enormous collection of possible universes with no clear mechanism for selecting which one is real. Some physicists responded by embracing the multiverse. If all possible string theory configurations exist as separate physical universes, and we happen to live in one that supports life, then our universe's properties are not predicted by the theory. They are selected by the fact that we can only live in a universe that allows life. This argument is called the anthropic principle. Critics find this deeply unsatisfying. A theory that predicts every possible universe effectively predicts nothing. If your framework is compatible with any outcome, it cannot be tested or falsified. It stops functioning as science in any meaningful sense. This debate has consumed enormous intellectual energy in theoretical physics for the past 3 decades. Supporters of string theory argue it remains the most mathematically rich and promising framework ever constructed. Critics argue it has become untestable speculation. Both sides are right about something. String theory's mathematics is extraordinary. Its connection to observable reality remains, after decades of work, unproven, and while physicists argue about extra dimensions and landscape problems, a separate crisis has been quietly building inside the quantum field equations themselves. A crisis that does not require extra dimensions or multiverses to produce its own brand of impossibility. A crisis that involves something called the spectral gap, and the discovery that certain quantum problems are mathematically impossible to solve, not because the calculations are hard, but because they are provably unanswerable. In 2015, a team of mathematicians proved something that stunned the physics community. They were studying a specific property of quantum systems called the spectral gap. The spectral gap is the energy difference between the ground state of a system, its lowest energy state, and the next energy state above it. Whether this gap exists or not determines how a material behaves. Superconductors have a gap. Metals do not. Whether a quantum material acts like an insulator or a conductor depends directly on its spectral gap. For decades, physicists assumed that given enough computing power and enough time, you could always calculate the spectral gap of any quantum system from its basic description. Hard? Yes. Impossible in practice for large systems? Yes. But theoretically solvable, always, the mathematicians proved this assumption was wrong. They showed that for generic quantum systems, the spectral gap problem is undecidable. That is a specific mathematical term with a precise meaning. An undecidable problem is one where no algorithm, no matter how sophisticated, running on no computer, no matter how powerful, can always produce the right answer. The problem is not just hard. It is provably, mathematically beyond the reach of any computable method. The proof connected quantum physics to a class of problems in mathematics called Turing undecidable, named after Alan Turing, the computer science pioneer. Turing showed in the 1930s that certain mathematical questions cannot be answered by any systematic procedure. The spectral gap problem, it turns out, belongs to that class. This has a disturbing implication. The Standard Model describes the behavior of matter using quantum fields. The ground state of those fields, the vacuum, has properties that are analogous to a spectral gap problem. If you scale up the undecidability result, it suggests that there may be fundamental properties of the quantum vacuum that are not just unknown, but unknowable through any mathematical procedure built on the current foundations of the theory. No one is claiming the universe is random or lawless. The undecidability result applies to certain generic quantum systems, not necessarily to the specific quantum fields of the Standard Model. Physicists are careful to note that it is not a direct proof of anything catastrophic. But it signals something important. The mathematical world that quantum field theory lives in contains regions where the tools of calculation simply stop working, where the questions cannot be answered through any algorithm, no matter how powerful. And inside the quantum field theory framework, physicists already knew of one place where they had been forced to use a mathematical tool so strange it required stepping outside normal time. Physics is built on real numbers. Distances are real, masses are real, Energies are real. So it is jarring, to put it mildly, that a core technique used in modern quantum field theory requires replacing real time with imaginary time. In mathematics, imaginary numbers are built from the square root of -1. They are called imaginary because no real measurement can produce the square root of a negative number. They exist as a mathematical tool, a way to handle certain equations that cannot be solved using only real numbers. They are extraordinarily useful in engineering, in signal processing, in electrical circuit design. But they are not time, they are not physical. In quantum field theory, physicists often need to calculate how a quantum system evolves and settles into its lowest energy state. The equations that govern this process are mathematically identical in structure to the equations that describe how heat spreads through a material over time, except for one crucial difference. The time variable in the quantum equations appears multiplied by the square root of -1, if you replace that imaginary time with real time. The equations for quantum field behavior and the equations for heat diffusion look identical. Physicists exploit this connection deliberately. They replace the imaginary time in their quantum equations with real time, solve the much easier heat diffusion version of the problem, and then try to translate the answer back into the original quantum language. This procedure is called a Wick rotation, named after the Italian physicist Giancarlo Wick. It sounds like a trick. It is a trick. But it works for many calculations. The problem is the translation step. Going from the imaginary time solution back to the real-time quantum answer introduces errors. The mathematical mapping between the two is not always clean. For simple systems in simple environments, the translation works well. For the complex quantum materials that physicists actually care about, like high-temperature superconductors, quantum magnets, and topological materials, the translation introduces exponentially large uncertainties. The answer you get back from the imaginary time detour may be close to correct, or it may be completely wrong, and you often have no reliable way to tell which. In 2021, researchers found that using specific mathematical functions called causal functions during the translation step could significantly reduce the errors. The improvement was real. But the fundamental problem remained. Quantum field theory, when applied to complex real-world materials, requires a mathematical detour through imaginary time, and that detour is imprecise in ways that affect real predictions for real experiments. Physics is having a conversation with imaginary numbers and struggling to translate what they say back into the language of the real world. And all of this, the vacuum catastrophe, the infinities, the undecidable spectral gap, the imaginary time detour, all of it may point toward the same conclusion, a conclusion that a growing number of physicists are starting to take seriously. Every successful theory in the history of physics eventually revealed its own limits. Newton's laws of motion worked perfectly for centuries. They built bridges, launched cannonballs, and sent ships across oceans. Then, Einstein showed that Newton's equations were an approximation. At speeds close to the speed of light or near very massive objects, Newton's numbers drift from reality. His equations are still useful within their range, they are just incomplete. Quantum field theory may follow the same pattern. A growing number of physicists believe quantum field theory is what they call an effective field theory. This is a technical term with a specific meaning. An effective theory is one that correctly describes nature within a certain range of energies, below a certain scale, and fails or becomes undefined beyond that scale. It is accurate within its domain. It is an approximation of something deeper outside that domain. The signals that quantum field theory might be an effective theory are everywhere in the framework itself. Renormalization requires adjusting the theory's parameters based on the energy scale at which you are working. Different energies require slightly different values. This energy dependence of the parameters is called running of the coupling constants, and it is built into how the theory operates. A truly fundamental theory, many physicists argue, should not have parameters that change with energy. A truly fundamental theory should derive everything from first principles. The vacuum catastrophe is the loudest signal. A fundamental theory should not predict that empty space contains energy 10 followed by 120 zeros times what we measure. An effective theory, one that breaks down at some high-energy scale, might produce that prediction because it is missing physics that operates at scales above its range of validity. The missing physics, if it existed, might cancel out the enormous predicted vacuum energy and leave behind only the tiny measured value. String theory is one candidate for the deeper theory that quantum field theory approximates. Others exist. Loop quantum gravity proposes a different mathematical framework. Post-quantum classical gravity suggests that gravity might not need quantum rules at all, that it operates by different mechanics than the other forces, and that trying to quantize gravity has been the wrong approach from the beginning. None of these alternatives has produced a complete, tested, verified theory. They are frameworks and research programs, not finished answers. What is remarkable is that physicists can hold this situation together at all. The theory they use every day to build particle accelerators and atomic clocks is, by their own analysis, either an approximation of something they have not found yet, or a framework sitting on unproven mathematical foundations, or both simultaneously. They use it anyway. Because it works within its range, and because, so far, nothing better has appeared. But what lies beyond that range, at the deepest levels of the quantum fields, at the smallest scales of space itself, is a place where the smooth, continuous fabric of space-time may dissolve into something unrecognizable, a churning, boiling structure called quantum foam. And the image it conjures changes everything about how you picture the ground beneath your feet. Zoom in on the floor beneath you. Past the wood or tile or concrete, past the molecules bonded together in their lattices, past the atoms, each one mostly empty space with a dense nucleus at the centre, past the protons and neutrons built from quarks, past the quarks themselves, bound in their unbreakable prison by gluon fields. Keep going. At some point you pass the scale where any existing instrument can follow. Particle accelerators probe down to scales about 100 million times smaller than an atom. Beyond that, nothing built by human hands can see. But the mathematics keeps going. At a scale roughly 100 billion times smaller than a proton, something extraordinary is predicted to happen. Physicists call this the Planck scale, named after Max Planck, whose work started the quantum revolution. At the Planck scale, the equations of quantum field theory and general relativity simultaneously break down. Neither framework can describe what is happening, both produce nonsense. But the math gives hints, and the hints describe something nothing like the smooth, quiet emptiness of everyday space. At the Planck scale, space-time itself is predicted to become a churning, violent foam, the quantum uncertainty that forces virtual particles to flicker in and out of the vacuum also applies to space-time itself. Space cannot sit still, it fluctuates. The geometry of space at that scale would jump and bubble and tear, constantly forming and dissolving tiny structures so extreme they defy normal description. Picture the surface of the ocean, seen from high altitude. From a plane, it looks flat and smooth. Drop down to the surface during a storm, and it becomes a violent, turbulent chaos of waves, foam, and spray. The Planck scale does to space roughly what a storm does to the ocean surface, except the violence is many orders of magnitude more extreme than any physical storm can produce. This quantum foam is a prediction. No one has ever measured it. The Planck scale is so far beyond current technology that no conceivable instrument within the next century has any chance of probing it directly. Some physicists have spent their careers trying to find indirect evidence. A few experiments have searched for tiny distortions in the arrival times of light from distant gamma-ray bursts, distortions that quantum foam might produce as photons travel across billions of light years. So far, no confirmed signal. But theoretically, the foam has consequences that go beyond being a strange feature of very small scales. If space-time is fundamentally grainy and turbulent at the Planck scale, then the assumption underlying all of quantum field theory, that fields spread smoothly through a continuous spacetime, is only approximately correct. Fields are not spreading through an infinitely smooth medium. They are spreading through something that looks smooth from far away, but is actually a seething structure at the deepest level. Every calculation done in quantum field theory assumes a smooth background. Every particle accelerator experiment, every prediction matched to 12 decimal places, every renormalized equation, all of it assumes that the stage the fields perform on is perfectly flat and continuous at small scales. If the stage is actually quantum foam, then all of those calculations are working on a simplified approximation of reality. A very accurate approximation, but an approximation nonetheless. And at the boundary where the foam begins, something else waits, something that connects quantum fields to the most extreme objects in the universe: black holes. Black holes do not just bend space, they swallow information. At least that is what the equations suggest. And if it is true, it breaks something fundamental about how quantum field theory works. Here is the setup. Quantum mechanics has a rule at its core. Information is never destroyed. If you burn a book, the physical information in those pages, the specific arrangement of atoms, the particular pattern of ink, all of it gets scrambled into smoke and ash and heat. It looks destroyed. But the information is technically still there, encoded in the precise positions and velocities and quantum states of every particle in the smoke. In principle, with perfect knowledge and perfect tools, you could work backward from the smoke and reconstruct the book. Quantum mechanics guarantees this. The total information content of a closed system is always preserved. Now take a black hole. A black hole has a boundary called the event horizon. Anything that crosses it, matter, light, radio waves, cannot escape. The gravity inside the event horizon is so extreme that even light, travelling at the fastest speed anything can move, cannot claw its way back out. In the 1970s, Stephen Hawking discovered something remarkable. Black holes are not perfectly black. Quantum field effects right at the event horizon cause the black hole to slowly radiate energy. Virtual particle pairs pop into existence at the horizon. One falls in, one escapes. Over an enormously long time, the black hole radiates energy and slowly shrinks. Eventually, it evaporates entirely. That radiation, called Hawking radiation, appears to be completely random. It carries no information about what fell into the black hole. If a book falls in and the black hole eventually evaporates, the Hawking radiation that comes out is indistinguishable from the radiation produced by a brick falling in. The information in the book appears to be gone forever. This is the black hole information paradox, and it creates a direct collision between quantum mechanics and general relativity. Quantum mechanics says information is never destroyed. General relativity plus quantum fields says black holes evaporate into structureless, information-free radiation. Both cannot be fully correct. Physicists have fought over this problem for 50 years. Some argue the information is secretly encoded in subtle correlations within the Hawking radiation, correlations so delicate that no realistic experiment could ever detect them. Others argue that information does escape through some mechanism not yet understood, perhaps through the quantum structure of spacetime at the Planck scale. Still others have proposed that black holes do not completely evaporate, but leave behind a stable remnant that stores the information forever. Each solution creates new problems. The information paradox has driven some of the deepest thinking in theoretical physics over the past 2 decades. It sits at the exact intersection of quantum field theory, general relativity, and thermodynamics, the 3 pillars of modern physics. The fact that they produce contradictory answers at the black hole horizon tells physicists that something fundamental is wrong with at least one of the frameworks. And the missing ingredient might be something that quantum field theory has no language for at all: what space and time actually are at the deepest level, beneath the foam, beneath the fields. The standard model has an asymmetry problem. a serious one. The equations of quantum field theory treat matter and antimatter almost identically. For every particle in the theory, there is a corresponding antiparticle with the opposite charge and the same mass. When a particle meets its antiparticle, they annihilate each other, converting completely into energy. In the earliest moments after the Big Bang, energy converted into particles. But quantum field theory predicts that energy should have created equal numbers of particles and antiparticles. One hydrogen atom for every antihydrogen atom. One electron for every positron. Perfect symmetry, perfect balance. If that had happened, every particle would have met its antiparticle partner and annihilated. The universe would contain nothing but radiation, light travelling in all directions through empty space. No atoms, no stars, no planets, no anything. And yet here we are. The observable universe contains roughly 10 followed by 80 atoms of ordinary matter. It contains, as far as any measurement has ever shown, almost no primordial antimatter at all. Something in the very early universe produced slightly more matter than antimatter. For every 1 billion antiparticles, there were approximately 1,000,000,001 particles. The antiparticles annihilated the particles one for one. The tiny surplus of 1 in a billion survived. That survivor is everything you have ever seen or touched. The Standard Model contains a mechanism for this imbalance. It is called CP violation, a slight difference in how the laws of physics treat matter and antimatter under certain conditions. But when physicists calculate how much matter the Standard Model CP violation would have generated, the number is far too small. The observed surplus of matter in the universe requires a degree of asymmetry that the Standard Model cannot produce. Something outside the Standard Model created the matter universe. Something the theory does not describe, does not predict, and does not have a place for. This is one of the deepest existential puzzles in physics. The existence of matter, every galaxy, every star, every living thing, depends on a physical process that the most complete theory of particles ever built cannot explain. The universe exists for a reason the equations cannot give. Physicists call this the baryogenesis problem, the problem of where the matter came from. Proposed solutions involve new particles, new forces, new symmetries, all operating at energies far above what any current accelerator can reach, all unconfirmed. The universe itself is evidence that the Standard Model is incomplete. You are that evidence. Your existence requires physics beyond the best framework humans have ever built. And there is something else hiding in plain sight inside the theory. A number. A specific measured number. A number with no explanation, no derivation, no origin story. A number that sits in the equations like a stranger in a family portrait, fitting perfectly while belonging to nothing. The Standard Model has 19 free parameters. A free parameter is a number that goes into the equations from outside. It is measured experimentally and plugged in. The theory does not predict it. It does not derive it. It simply requires it, the way a calculator requires you to type in the numbers before it can give you an answer. These 19 numbers include the masses of all the fundamental particles, the strengths of the three forces described by the Standard Model, and several other quantities related to how particles mix and interact. Every one of them has been measured with impressive precision. Every one of them must be set by hand. A truly fundamental theory, one that genuinely starts from first principles, should not have free parameters. It should derive everything it needs from the structure of the theory itself. The speed of light appears in the theory, but it is not a free parameter. It defines the structure of space-time, and cannot be otherwise, without changing the nature of reality. The free parameters are different. They are numbers that could, mathematically speaking, be almost anything. They happen to take specific values in our universe. The theory does not explain why. Consider the mass of the electron. It is extremely small compared to the next lightest particle, about 200 times lighter than the muon, which appears to be a heavier copy of the electron with no known purpose. Why is the electron so light? Why does the muon exist at all? The standard model has no answer. Both masses are measured and plugged in. The theory accepts them without explanation. Consider the strength of the strong nuclear force. If it were slightly weaker, protons and neutrons would not bind into atomic nuclei. Hydrogen would be the only element. No carbon, no oxygen, no chemistry, no biology. If it were slightly stronger, protons would fuse so readily that all hydrogen would have burned up in the early universe. Again, no stars. The force has the exact strength required for complex chemistry to exist, and the standard model does not explain why it has that strength. It simply measures it and uses it. This situation troubles physicists deeply. The 19 parameters look finely tuned. They look chosen. Several of them sit in narrow ranges where, if they shifted only slightly, the universe would be sterile and structureless. Some physicists see evidence of a deeper theory in this, one that derives the parameters rather than accepting them. String theory was expected to do this. It has not yet managed it. Others invoke the multiverse again, arguing that across the enormous landscape of possible universes, some will have parameters compatible with life. And those are the only universes anyone can observe. That argument is logically valid and scientifically untestable. The 19 numbers sit in the equations of the most successful theory in science, and the theory that contains them has no idea where they came from. Something even stranger waits in the equations themselves, not in the numbers but in the structure. A structure that some physicists believe is hiding a perfect, invisible symmetry that could, if it exists, solve the vacuum catastrophe in a single stroke. The vacuum catastrophe produces a prediction 120 orders of magnitude too large. That gap is so enormous that most physicists assume it cannot be an accident. Something must be cancelling out the vacuum energy. The question is what? In the 1970s and 80s, physicists developed an idea that would handle the cancellation automatically, without requiring any fine-tuning. The idea was called supersymmetry. Supersymmetry proposes that nature has a perfect mirror. Every particle that exists has a partner particle, a superpartner, with slightly different properties. The electron has a superpartner called the selectron. The quark has a squark. The photon has a photino. These partners have never been observed. But if they exist, their contributions to the quantum vacuum energy would cancel precisely against the contributions of ordinary particles. The boiling activity of virtual particles and their superpartners would balance to nearly zero, solving the vacuum catastrophe without any mysterious adjustment required. The symmetry between ordinary particles and their superpartners is what physicists call supersymmetry. If it is exact and unbroken, the cancellation is perfect. The vacuum energy is exactly zero. The measured vacuum energy is tiny but real. So supersymmetry, if it exists, must be a broken symmetry. It operated perfectly in the earliest moments of the universe and then broke as the universe cooled. That breaking left a small residue of vacuum energy, the dark energy we measure today. The breaking also means the superpartner particles should have masses different from their ordinary partners, heavy enough to have escaped detection so far, but light enough to appear at the energies probed by the Large Hadron Collider. The Large Hadron Collider ran experiments specifically designed to find them. It smashed protons together at energies higher than any machine in history. The analysis of those collisions produced a clear result. No superpartner particles appeared. The search has been extended and extended again. Still nothing. This does not prove supersymmetry is wrong. The superpartners could be heavier than the collider can reach, but the heavier the superpartners are, the more the cancellation is imperfect, and the more the vacuum catastrophe requires a different explanation. Supersymmetry remains mathematically beautiful, it remains theoretically compelling, and it remains, after decades of searching, experimentally invisible. If supersymmetry does not exist, then the cancellation of vacuum energy was either an enormous coincidence or the result of some other mechanism that physics has not discovered yet. The problem stays open. the prize for solving it stays unclaimed. And all of this trouble with the vacuum, with the energy of empty space, connects back to something you can actually see, something expanding right now in every direction around you. The universe is getting bigger. Not slowly, not gradually settling towards some steady state. Faster. The rate of expansion is increasing. Every galaxy not bound to our local group is moving away from us, and moving away faster than it was 1 billion years ago, and faster still than it was 2 billion years ago. The expansion is accelerating. Something is pushing it. That something is dark energy. Dark energy makes up roughly 68% of the total energy content of the universe. It is the dominant component of everything that exists. It is also completely absent from the Standard Model. It was not predicted by quantum field theory. It was discovered in 1998, when 2 separate teams of astronomers studying distant exploding stars called supernovae independently found that the universe was not slowing down as expected. It was speeding up. The discovery earned a Nobel Prize. It also landed physics in a profound crisis. The simplest explanation for dark energy is that empty space has a constant energy density. More space means more total energy. As the universe expands and creates more space, the total amount of dark energy grows. This growing energy drives the acceleration. Einstein had actually introduced a term for exactly this kind of energy density in his equations, called the cosmological constant. He later removed it, calling it his greatest blunder. Observations in 1998 showed he was right the first time. The cosmological constant fits the data beautifully. The problem is what quantum field theory predicts its value should be. The vacuum energy calculation, the one that produces the number 10 followed by 120 zeros too large, is effectively a prediction of the cosmological constant from quantum fields. The prediction is catastrophically wrong. The measured value of the cosmological constant is real, tiny, and constant across the universe. The quantum field prediction of the vacuum energy is real, enormous, and should have destroyed the universe before it began. Something cancels out nearly all of the predicted vacuum energy, leaving only the tiny measured cosmological constant behind. Some physicists have proposed that dark energy is not a constant but changes over time, a field called quintessence that slowly evolves. If true, the dark energy density would have been different in the past and will be different in the future. Current measurements can only barely distinguish between a true constant and a slowly evolving field, and the evidence so far is consistent with either. Other physicists argue that dark energy itself is evidence that general relativity breaks down on the largest scales, that gravity behaves differently across billions of light years than it does in our local neighbourhood. Modified gravity theories exist. None has matched all the data better than the simple cosmological constant. The universe is telling us something through its accelerating expansion. It is powered by an energy that fills empty space, connects directly to the broken vacuum prediction, and has no satisfactory explanation in any current theory. And the matter we can see, making up only 5% of the universe's total content, has its own missing piece, a vast invisible component surrounding every galaxy, bending light, shaping structure, and leaving no trace in the Standard Model's equations. Galaxies spin too fast. In the 1970s, astronomer Vera Rubin measured the rotation of spiral galaxies. The outer edges of a galaxy should orbit the centre more slowly than the inner regions, just as the outer planets of the solar system orbit the Sun more slowly than the inner ones. This follows directly from gravity and the distribution of visible mass. Rubin found the opposite. Outer regions of galaxies rotate at roughly the same speed as the inner regions. The rotation curves are flat where they should be declining. Something is adding extra gravitational pull at the outskirts, where there is little visible matter. That something is dark matter. It does not emit light. It does not absorb light. It does not interact with the electromagnetic field at all, which is why no telescope can see it directly. It only reveals itself through gravity, by pulling on ordinary matter in ways that do not match what visible mass alone would produce. Dark matter makes up roughly 27% of the universe's total energy content. It outweighs ordinary matter 5 to 1. Every galaxy sits inside a vast halo of dark matter, stretching far beyond its visible edge. The galaxies we see are islands inside invisible clouds of something the Standard Model cannot describe. The evidence for dark matter comes from multiple independent sources. Rotation curves like Rubin's observations, the way clusters of galaxies bend light from objects behind them, an effect called gravitational lensing, the pattern of temperature variations in the faint afterglow radiation left over from the Big Bang, computer simulations of how the large-scale structure of the universe forms over time. All of them point to a massive, invisible, non-interacting substance distributed throughout the cosmos. The Standard Model has no particle that fits the description. Every particle it contains either interacts electromagnetically, like electrons and quarks, or has been ruled out as a dark matter candidate by experiment. Dark matter requires something new, something outside the framework. Physicists have proposed dozens of candidates. Weakly interacting massive particles predicted by supersymmetry were the leading candidate for decades. Underground detectors filled with liquid xenon and cooled to temperatures colder than deep space searched for the faint signal of a dark matter particle occasionally bumping into a nucleus. Year after year, the detectors found nothing. The most sensitive instruments ever built for this purpose have now ruled out the most commonly expected versions of those particles. Axions are another candidate, extremely light particles predicted by a separate solution to a different problem in quantum chromodynamics. Axion searches are underway, no confirmed detection yet. Primordial black holes formed in the very early universe before stars existed have been proposed. Gravitational wave detectors have constrained but not eliminated this possibility. Dark matter is one of the most well-established facts in modern cosmology, and it is one of the most complete failures of the Standard Model. The universe is mostly made of things the theory cannot see, cannot predict, and cannot explain. The visible 5% of reality, the atoms and light that physics describes so precisely, sits inside a universe where the majority of everything is invisible. That is the territory quantum field theory covers. 5% hold a small magnet over a paperclip. The magnet picks it up, a small magnet generating a tiny magnetic field with a handful of electrons worth of current, just overpowered the gravitational pull of the entire Earth on that paperclip. The electromagnetic force from that magnet beat the gravity of a planet with a mass of 6 trillion kilograms. Gravity is extraordinarily weak compared to every other force. This is not a rough comparison, it is a precise one. The electromagnetic force between two electrons is approximately 10 followed by 40, 2 times stronger than the gravitational force between them. 42 orders of magnitude. That gap is so extreme it has its own name. Physicists call it the hierarchy problem. The hierarchy problem goes deeper than just observing the gap. The Standard Model's equations include a parameter called the Higgs mass, the mass of the Higgs boson. This mass determines the masses of every other fundamental particle through the Higgs mechanism, and the Higgs mass is extremely small compared to the energy scales where the Standard Model is expected to break down. Quantum field theory predicts that the Higgs mass should receive enormous corrections from virtual particle interactions at high energies. These corrections naturally push the Higgs mass up toward the highest energy scales in the theory. But the measured Higgs mass is small. To keep it small, the enormous upward correction has to be almost perfectly cancelled by an equally enormous downward correction. The cancellation required is accurate to 30 or more decimal places, depending on how high in energy you trust the theory. This kind of cancellation, like the vacuum energy cancellation, is not impossible. But it looks unnatural. It looks like the equations are being forced into an unlikely configuration by something outside themselves. Supersymmetry was supposed to solve this problem too. The superpartner particles would naturally cancel the large corrections to the Higgs mass without requiring any fine-tuning. The cancellation would be automatic and elegant. This was actually the primary motivation for building the Large Hadron Collider. Finding the Higgs boson was the headline achievement. Finding superpartner particles was the expected bonus that would resolve the hierarchy problem. The Higgs boson was found in 2012, exactly as predicted. The superpartners were not found, and have not been found, and the hierarchy problem remains open. Gravity is absurdly weak. The Higgs mass is absurdly small. Both require enormous cancellations with no explanation, and both problems point at the same suspicion: the standard model is tuned in ways that require physics beyond itself. Physics that so far nobody has found. The hierarchy problem is uncomfortable because of how it looks. It looks like someone adjusted the dials of the universe by hand. It looks designed. That appearance is disturbing to scientists because science depends on the assumption that the universe follows consistent rules that nature generates on its own without a dial turner. Whether the universe actually was tuned, or whether a deeper theory will explain the tuning naturally, is one of the open questions defining physics right now. And the answer, if it ever comes, may require a completely different mathematical structure than anything quantum field theory currently uses. String theory is not the only attempt to fix the broken foundations of quantum field theory and merge gravity with quantum mechanics. Another approach, called loop quantum gravity, proposes something radically different. It does not add dimensions. It does not replace particles with strings. It takes the structure of space itself and breaks it into discrete pieces. The core idea goes like this. General relativity says space-time is a smooth, continuous fabric that bends and stretches. Quantum mechanics says everything at small scales comes in minimum units. Energy is quantized. Charge is quantized. Angular momentum is quantized. Loop quantum gravity says space-time is quantized too. In this framework, space does not exist as a smooth continuum. It is made of tiny, discrete chunks called spin networks. Imagine space as a fabric, and then zoom in until the continuous threads reveal themselves as individual fibers. Each fiber has a minimum thickness. You cannot cut it smaller. Space is not infinitely divisible. It comes in grains. The minimum grain of space in loop quantum gravity has a size at the Planck scale, the same scale where quantum foam is predicted to appear. Below that size, the concept of space loses meaning. There is no space smaller than the grain. Space does not exist at distances shorter than the Planck length. This approach has an immediate consequence for the infinity problem in gravity. When physicists try to describe quantum gravity using standard quantum field theory, the infinities come from physics at arbitrarily small distances. Particles interacting over zero distance produce infinite answers. If space has a minimum grain size, there is no such thing as zero distance. The infinities are cut off by the graininess of space itself. Loop quantum gravity handles the infinities of quantum gravity without requiring extra dimensions, without replacing particles with strings, and without introducing superpartner particles. It works directly with the structure of spacetime as defined by general relativity, then quantizes that structure. The problems are deep. Loop quantum gravity is mathematically consistent in several limited regimes, but it has not yet produced a complete working theory that reproduces general relativity smoothly at large scales and quantum field theory at small scales simultaneously. It has not produced testable predictions that differ from current theories in any way that existing or near-future instruments could measure. String theory and loop quantum gravity represent the two most developed approaches to quantum gravity. Both have been worked on for decades by large communities of brilliant researchers. Both have achieved significant mathematical results. Neither has produced a tested, confirmed theory that resolves the foundational problems of quantum field theory. The race to find the next level of physics has been running for over 50 years. And the prize, a complete description of reality from the smallest Planck scale grain of space to the largest cosmic structure, remains unclaimed. The search has produced unexpected discoveries along the way. One of them involves a strange connection between quantum fields and the boundaries of space. A connection so surprising that when it was first proposed, many physicists assumed it had to be wrong. The universe might be a projection. That sounds like philosophy. It is physics. A specific, mathematically grounded proposal that has been one of the most intensely studied ideas in theoretical physics for almost 30 years. In the mid-1990s, physicist Juan Maldacena discovered something unexpected while studying a particular version of string theory. He found a precise mathematical equivalence between a quantum field theory living on a flat surface and a theory of gravity operating in a three-dimensional space, one dimension higher. The gravity theory and the quantum field theory described exactly the same physics. Every calculation in one had a corresponding calculation in the other. They were two different languages for the same reality. This equivalence is called the anti-de Sitter conformal field theory correspondence, or the holographic principle. The name comes from a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. In Maldacena's correspondence, a lower-dimensional quantum theory on a boundary encodes all the physics of a higher-dimensional space inside. The implication is striking. The three dimensions of space you move through every day might themselves be a kind of projection. The information required to describe everything happening in the volume of a region of space might be fully encoded in the boundary surrounding that region, in a lower dimensional description without gravity. This is not just an analogy. The mathematical correspondence is exact. Calculations that are impossibly difficult in the gravity theory can sometimes be translated into calculations in the quantum field theory that are straightforward. Physicists have used this translation to study the behavior of hot, dense matter in conditions similar to the early universe and the interior of neutron stars, conditions impossible to reproduce in the laboratory. The holographic principle has also been applied to the black hole information paradox. If the information that falls into a black hole is encoded on the black hole's boundary surface, and if the boundary theory is a quantum field theory with no information loss, then information is preserved. The holographic correspondence suggests a resolution: information is not destroyed, just encoded differently. This resolution requires accepting that the three-dimensional interior of the black hole is, in some sense, secondary. The real description lives on the boundary. The interior is the projection. The holographic principle does not mean reality is fake. It means the relationship between space, volume, and information is far stranger than classical physics suggested. The number of bits required to describe a region of space scales with the area of its boundary surface, not with its volume. Information in the universe is stored on surfaces, not in depths. No experiment has directly tested the holographic principle. It emerged from string theory, which itself remains experimentally unconfirmed. But the mathematical tools it has produced have proven useful across multiple areas of physics, from condensed matter to black hole thermodynamics to quantum information theory. Reality might have fewer dimensions than it appears to. The equations might be telling us something profound about what space actually is. And all of these mysteries, the infinities, the vacuum catastrophe, the gravity problem, the missing dimensions, the invisible matter and energy, circle back to the same question. The question that motivated quantum field theory from the very beginning. What are things, at the most fundamental level, made of? Every theory physicists have built so far treats quantum fields as fundamental. The electron field exists. The electromagnetic field exists. The Higgs field exists. They are the bedrock. The particles we observe are ripples in these fields, and the fields themselves are the deepest level of reality the current framework can describe. But a growing suspicion in theoretical physics asks whether the fields themselves are built from something even more basic. This is not a new pattern in science. Atoms were once considered fundamental, the irreducible building blocks of matter. Then physicists discovered atoms are built from electrons, protons, and neutrons. Protons and neutrons turned out to be built from quarks. Quarks, as far as any experiment can tell, are structureless points with no internal parts. But quarks only exist because of the quark field, and the quark field by current understanding is fundamental. Or is it? Some approaches to quantum gravity suggest that space-time itself is built from quantum entanglement. Entanglement is a quantum phenomenon where two particles become linked in such a way that measuring one instantly determines the state of the other, regardless of distance. Einstein called it spooky action at a distance. In quantum information theory, entanglement is the fundamental resource that powers quantum computers and quantum cryptography. Certain calculations in the holographic framework suggest that the smooth spacetime of general relativity emerges from the entanglement structure of a quantum system on a boundary. The geometry of space, including its dimensions and its curvature, is encoded in patterns of entanglement. Pull two regions of the boundary apart in entanglement terms, and the corresponding regions of the interior space become geometrically disconnected. If this picture is correct, then spacetime is not fundamental. Spacetime is an emergent structure built from the entanglement of something more basic. And if spacetime is emergent, then the quantum fields that live on spacetime are also emergent. Everything quantum field theory describes, every particle, every force, every field, is a higher-level description of something operating beneath it. This idea is called emergent spacetime, and it is one of the most active and contested areas of theoretical physics. It is not confirmed. It is not even close to a complete theory, but the mathematical signals pointing toward it are appearing in multiple independent frameworks, from string theory to loop quantum gravity to quantum information theory. The possibility that the fields of quantum field theory are themselves built from something deeper, the way atoms are built from quarks, is one that physicists are taking more seriously every year. And if the fields are emergent, then the infinities, the vacuum catastrophe, the gravity problem, and the mathematical breakdowns in the current framework might all have a single source. The framework might be breaking down exactly where it is, trying to describe the level of reality below its own foundation. That foundation, whatever it turns out to be, may require tools and concepts that do not yet exist, which raises the most unsettling question of all. Science has a history of replacements. Newton's mechanics was replaced, inside its limits and beyond them, by relativity and quantum mechanics. The old framework did not disappear. It became an approximation, accurate within its range, outdated outside it. Newton's equations still land spacecraft on Mars. They simply do not describe what happens near black holes or inside atoms. The standard model will likely follow the same path. It is accurate within its range. It matches experiments to extraordinary precision. And it breaks down at the edges of that range in ways that physicists have mapped carefully. The question of what replaces it, what the next framework looks like, has produced dozens of proposals and no confirmed answers. Grand unified theories attempt to merge the three forces of the standard model, electromagnetism and the two nuclear forces, into a single force that splits apart at lower energies. Some versions of these theories predict that protons are not stable. They should decay over an almost incomprehensibly long time, roughly 10 followed by 34 years, far longer than the current age of the universe. But enormous tanks of purified water, buried underground and watched by thousands of light detectors, have searched for this decay for decades. No proton decay has been observed. The simplest grand unified theories have been ruled out by this absence. Technicolor theories propose that the Higgs boson was not a fundamental particle, but a composite structure built from new particles bound by a new force. The discovery of the Higgs boson in 2012 showed it behaves like a fundamental particle, not a composite. Most Technicolor models have been ruled out. Extra dimension theories, beyond those in string theory, proposed that gravity leaks into additional spatial dimensions, explaining why it is so much weaker than the other forces. Experiments at the Large Hadron Collider and gravitational wave detectors have constrained but not eliminated certain versions of these models. Every proposed extension of the standard model has a signature, a specific prediction that distinguishes it from the standard model alone. So far, every search for those signatures at the Large Hadron Collider has come up empty. The Higgs boson was found exactly as predicted. Nothing else was. The Standard Model, broken as its foundations are, continues to describe every experiment we can perform with perfect precision. This situation is called the nightmare scenario by some physicists. The Standard Model is wrong at a deep level, but right at every scale we can currently probe. The physics beyond it hides at energies too high for existing accelerators to reach. Future machines, larger and more powerful, might reach those energies, or the signature of new physics might appear in precision measurements rather than direct particle production. The search continues. The silence from the data continues alongside it. But the problem is larger than finding new particles. The deeper problem is mathematical. The Standard Model's foundations are unproven. The equations work without a proof that they should work. And the $1 million prize sitting on that proof is a symbol of how incomplete the understanding actually is. Mathematics is the language of physics. When physics works, mathematics describes it. When physics breaks down, the mathematics breaks down alongside it. And sometimes, mathematics breaks down in ways that reveal not just a technical difficulty, but a fundamental limit on what can be known. The spectral gap result from 2015 was one such limit. A specific class of quantum problems is provably undecidable. No algorithm can always produce the correct answer. The problem belongs to a category of questions that lie beyond the reach of systematic computation. This result has a precise mathematical statement and a rigorous proof. It is not a numerical difficulty or a computational bottleneck. It is a logical wall. Certain quantum systems simply cannot be analysed by any rule-following procedure, no matter how clever or how powerful. Physicists and mathematicians have long known that quantum many-body problems involving large numbers of interacting quantum particles, are extraordinarily difficult. The computational resources required to simulate even a modest quantum system exactly grow exponentially with the system size. A quantum system of a few hundred particles already requires more memory than exists in all the computers on Earth combined. Quantum computers are being built to address this. A quantum computer uses quantum phenomena, superposition and entanglement, to perform calculations that classical computers cannot. For simulating quantum systems, a quantum computer of sufficient size would be exponentially faster than any classical machine. But the undecidability result applies even to quantum computers. An undecidable problem remains undecidable whether the computer running the calculation is classical or quantum. The wall is not computational power, it is logical structure. The practical impact on quantum field theory is not fully mapped. The specific systems shown to be undecidable are generic quantum lattice models, not necessarily the exact quantum fields of the Standard Model. But the proof establishes that the mathematical world containing quantum field theory has regions where systematic knowledge breaks down entirely. Physics has hit mathematical walls before. The three-body problem in classical gravity has no general analytical solution. The behaviour of turbulent fluids cannot be derived from first principles for complex cases. These are hard problems. Difficult, possibly intractable in practice, but theoretically answerable with enough information and computation. Undecidable problems are different. They are not hard. They are provably unanswerable. No amount of cleverness or computing power resolves them. They represent regions of the mathematical universe where knowledge, defined as the output of any systematic procedure, simply does not reach. Quantum mechanics lives in that universe, and some of its most natural questions live in those unreachable regions. This should be the final word on the limits of knowledge in physics. A mathematical proof that some things cannot be known, except that physics is already pushing beyond those limits in unexpected ways. Experiments that probe the foundations of quantum field theory have started producing results that sit in the gap between theory and reality, in the places where the approximations might be showing their edges. One of those experiments involves the muon, a particle nobody asked for, that appeared in cosmic ray data in the 1930s and prompted one physicist to ask, famously, who ordered that? The muon is the electron's strange twin. It has exactly the same charge as an electron. It interacts with every force exactly the way an electron does. Its only difference is mass. The muon is about 200 times heavier than the electron. It is unstable, decaying into other particles after a tiny fraction of a second. No atom in nature contains a muon. No chemistry involves it. It appears in cosmic ray showers when high-energy particles from space hit the upper atmosphere, and it appears in particle accelerators, and it plays no known role in the structure of the universe. Its existence is a mystery the Standard Model accepts without explanation. There are actually 3 generations of matter particles in the model. The electron, the muon, and the tau particle are all essentially identical except for their masses, increasing by large factors with each generation. The quarks come in 3 generations too. Why 3? The Standard Model has no answer. It simply observes the pattern and codifies it. But the muon has become the centre of one of the most closely watched experiments in modern particle physics, because the muon wobbles. Like the electron, the muon behaves as a tiny spinning magnet. That spin causes it to wobble, the way a spinning top wobbles as it slows. The rate of that wobble is called the anomalous magnetic moment of the muon. It is precisely predicted by the Standard Model, just as the electron's magnetic moment is precisely predicted. And the measurement does not match. 2 independent experimental programs, one at Brookhaven National Laboratory completed in the early 2000s, and a more recent and more precise experiment at Fermilab, have both measured the muon's wobble rate. Both measurements agree with each other, both disagree with the Standard Model prediction. The disagreement is small in absolute terms, but in physics, small discrepancies that appear consistently across independent experiments are taken very seriously. The chance that the Fermilab result is a statistical accident is extremely low. The Standard Model predicts a specific wobble rate. The muon actually wobbles slightly faster. Something is giving the muon a small extra push, something interacting with it that the Standard Model does not account for. Every particle in the vicinity of the muon contributes to its wobble through quantum field effects. Virtual particles pop in and out of the vacuum around the muon and affect its magnetic properties. If there are particles beyond the Standard Model, their virtual contributions would alter the wobble rate. The discrepancy would be evidence of new physics. The muon anomaly is not confirmed as definitive new physics yet. Matching the experimental measurement requires an extremely precise calculation of the Standard Model's prediction, and different theoretical methods have produced slightly different predicted values. The experimental and theoretical communities have been working to nail down both sides of the comparison, but the signal has held up across 2 different experiments and 2 decades. The wobble of one unstable particle, 200 times heavier than an electron and gone in microseconds, may be the first crack in the wall of the Standard Model. If it is, whatever breaks through that crack will have to answer all the questions that quantum field theory cannot. The vacuum catastrophe, the infinities, the missing gravity, the 19 free parameters, the matter-antimatter asymmetry, the dark matter, the dark energy. The entire broken and magnificent structure waits for its successor. Physicists dream of a final theory, a framework that derives every particle mass, every force strength, every constant of nature from first principles. A framework where the 19 free parameters of the Standard Model are not plugged in from outside, but fall out of the equations as necessary consequences of the underlying structure. A framework that includes gravity without producing infinities, describes the vacuum without the catastrophic energy mismatch, and explains why matter dominates over antimatter. That framework does not exist, but physicists have a rough picture of what it would need to accomplish. It would need to be finite. Every calculation in the theory, at every energy scale, at every distance, should produce a finite, meaningful answer without requiring renormalization patches or energy cutoffs. The infinities that plague current quantum field theory would be absent, because the underlying structure of the theory would not allow them to appear. It would need to include gravity naturally. The way string theory's vibrating strings produce the graviton automatically. A complete theory should incorporate gravitational interaction as a consequence of the theory's structure, not as an afterthought added by hand. And unlike string theory's current form, the theory should do this in a regime that can be tested. It would need to predict rather than accept. A complete theory derives its parameters. It does not set the electron mass by measuring it and plugging it in. It demonstrates from its fundamental structure why the electron has exactly the mass it has, why the strong force has exactly the strength it has, why the cosmological constant is exactly the tiny value it is. It would need to solve the matter-antimatter asymmetry. It would contain the mechanism that tipped the early universe toward matter, built into its foundational equations. It would identify dark matter. The particle or collection of particles making up 27% of the universe would appear naturally in the theory's particle content, with properties that match every observation. It would explain the hierarchy problem. The extreme weakness of gravity compared to the other forces would follow from the theory's structure without requiring enormous coincidental cancellations. And perhaps most radically, it might change the picture of what space and time are. If the holographic principle is correct, if space-time is emergent from entanglement, then a complete theory of physics would not assume space-time as a background. It would derive space-time from something more fundamental. The smooth four-dimensional stage on which fields currently perform would itself be a consequence of the theory, not its setting. No one knows what such a theory would look like mathematically. The tools to write it down may not exist yet, just as the mathematics of general relativity did not exist before Einstein needed it, just as the calculus needed for Newtonian mechanics had to be invented alongside the physics. The history of physics suggests that every fundamental breakthrough required new mathematics. Calculus, non-Euclidean geometry, group theory, complex analysis. Each time the physical intuition came first, and the mathematical machinery had to be built to follow it. The next leap may be the same. The intuition that quantum field theory is broken at its foundations, that something deeper is waiting, may be correct. The mathematics to describe that deeper level may require tools that do not yet exist. That is an uncomfortable place to stand. It is also exactly where every major advance in physics has started. Every device you own runs on quantum field theory. The transistors in your phone operate because engineers understand quantum mechanics well enough to control electrons in semiconductors. The processors in every computer, the lasers in every fiber optic cable, the atomic clocks that make GPS accurate to within feet, all of it built on equations that physicists themselves call broken. The MRI machine at the hospital uses nuclear magnetic resonance, a direct application of quantum field theory. The solar panels converting sunlight to electricity depend on the photoelectric effect, which quantum field theory describes precisely. Particle accelerators using these equations have produced medicines for cancer treatment. Every material science discovery of the past 70 years rests on the quantum field framework in some form. The theory works staggeringly well. Within its range, at energies and scales accessible to human technology, its predictions are essentially perfect. The 12 decimal place electron calculation is not a party trick. It is a demonstration that something fundamental and real is captured by the equations. And yet, the foundations are cracked. The vacuum catastrophe remains unexplained. The infinities remain patched rather than solved. Gravity remains outside the framework. The mathematical proof that the core equations are even self-consistent remains unclaimed and worth $1 million. Dark matter and dark energy, representing 95% of the universe, have no place in the standard model. The matter-antimatter asymmetry has no explanation. The 19 free parameters have no derivation. Physics stands in the same position it has stood several times before. in possession of a framework that explains everything within reach, and aware with increasing clarity that beyond that reach something different is operating, something the current tools cannot touch. The history of physics says this gap does not stay open forever. Newton's mechanics ruled for 200 years before relativity and quantum theory replaced and extended it. The new frameworks built on the old ones absorbed what worked and described what the old frameworks could not. The Standard Model has ruled for 50 years. The pressure on its edges is growing. The muons wobble at Fermilab may be the first signal. Gravitational wave detectors are opening a new window on the most extreme physics in the universe. Future particle accelerators, if they are built, will probe energies the Large Hadron Collider cannot reach. Quantum computers are beginning to simulate quantum systems in ways classical machines never could, and those simulations may reveal the signature of new physics in condensed matter systems accessible on a lab bench. The next theory, whatever it is, will have been built on top of the broken and magnificent structure of quantum field theory. Every insight, every confirmed prediction, every 12 decimal place miracle will be part of the foundation of whatever comes next, the way Newtonian orbits are part of the foundation of general relativity. The equations are broken. The framework is incomplete. The universe, for all its vast, dark complexity, keeps running perfectly regardless. And somewhere in the gap between what the equations say and what the universe actually does, the next great theory of everything is waiting to be found.